Hello class, and welcome to section 3.6, which is about analyzing lines of fit. By the end of today's lesson, you will have an understanding of correlation coefficients, you will be able to create and interpret residual plots, and you will be able to interpret and use lines of fit to make predictions. A lot of vocab going on today. Line of fit, which we talked about a little bit in section 3.5. That is a linear model that can be used to establish correlation between data sets. In this case, we're going to be talking about lines of best fit, which is going to be a computer-generated model, as opposed to 3.5, where we were using our own lines of fit and drawing those in and making our own predictions. This is a computer-generated model to be as accurate as possible. Correlation coefficients, that's a number between -1 and 1. That is going to indicate the direction and strength of a linear relationship. We're going to dive into that a little bit deeper in a few moments. Residuals, this is the difference between a predicted y value and an actual y value. So once we have our linear model, our line of best fit, we're going to be able to make predictions. And then in order to compare the prediction with the original value with any given data point, we call that the residual. When we are making our predictions, if that prediction is falling within the given data set, we call that interpolation. So if our data set is between 0 and 10, 7, a prediction for the data value of 7 would be in between our inputs, so that's going to be interpolation. On the flip side of that, we've got extrapolation, which means it falls outside of the given data set. So again, if we were looking at 0 to 10, making a prediction for the value of 20, would be outside of our original set, so it's extrapolation. The last thing is causation. This means that the domain and range have a cause and effect relationship. So everything that we are inputting into the relationship would have a direct cause on the output of that relationship. So the inputs would be directly causing the outputs. Starting to dig a little deeper into these correlation coefficients, you can see we start at -1 and we run all the way up to 1. This is used to show how accurately a linear model is going to predict the data or how tightly those two concepts are related. So starting with -1, that means it's a perfect negative relationship. That means all of the values are in a perfect line going down negatively. When we get to in between -1 and -0.5, that's going to be a strong negative relationship. That means the data sets are likely related in a negative manner, and there's a solid chance that we can use that as an accurate model. Around -1/2, kind of plus or minus a little bit, that's going to be what we call a medium negative relationship. It's okay sometimes to use this as prediction, not all the time. If going from -5 down to 0, that's going to be a weak negative correlation. So the data are kind of related in a kind of negative manner, but it's not going to be very helpful for predictions. This no correlation, we call that a correlation coefficient of 0. The data is not related. The weak positive is going to go between 0 and 1/2. The data is kind of related in a positive manner. Again, right around 1/2, we could say that that's a medium positive correlation, about 50% accurate. Between 1/2 and going up to 1, that's going to be a strong positive correlation. And then right at 1, that's again that perfect. The points line up exactly in a straight line, and it is a positive straight line. So using these values, this first one, what does r equals 0.1 mean? R is the letter that we use for correlation coefficient. So if we go back, 0.1 is going to fall pretty close to 0, but it is a positive value. So we are going to say a weak positive correlation. So it is going to be a very weak correlation because we are super close to 0, but it does have some sort of a positive indication because our R value is positive. For our second one here, what does R equals -0.935 mean? That's super close to -1. So this would mean a strong negative correlation. So strong negative correlation. So when you are using a correlation coefficient, your goal is to decide the strength, so strong, weak, or medium, and then the direction, positive or negative. Obviously, if it's 0, then you would say no correlation. Go ahead and try this one on your own. An R value of 0.546 is going to be a medium positive correlation, about halfway in between, so we're going to call that medium, and it's positive. The next thing we're going to talk about is residuals and finding those residual values. Remember, residuals are how far away we are between our prediction and the actual value. So, what we have here is a linear model of y equals 0.5x plus 12.6. That's the model that our computer has generated for us that supposedly fits this data. In order to find the residuals, we're going to plug in and find the difference between the prediction and the actual value. So, if we're looking at this first point, we want our actual value is 11. We need to figure out our prediction value. In order to figure out the prediction, we're going to plug our x into our equation. So we're going to have, for 10, I'm going to say my residual is equal to 11, which is my actual value, minus my predicted value, which is going to be 0.5 times 10 plus 12.6. It is crucial that you have those parentheses around your predicted value so that we actually find this is going to calculate the predicted value, and then we're going to subtract it from our original value. And that's going to give me negative 2.1. You could type in and find 0.5 times 10 and then add your 12.6. So 0.5 is going to give you 0.5 plus 12.6, which is going to give you 13.1. 11 minus 13.1 is going to give you negative 2.1. So you could solve this first and do the subtracting, or you can write it out as one whole thing and type it into your calculator that way. The next one, for 15, we've got our actual value of 14, and subtracting off our predicted value, we're going to plug in 15 this time, and that's going to give us a value of 0.65. And then for 20, again, our actual value, and then subtracting off our predicted value, and that is going to give me an answer of 2.4. Go ahead and predict find the residual for 25 and 30 on your own. For 25, our residual is 1.15, and for 30, we get negative 2.1 again. The next thing we can do with our residual values is put them into a graph. These graphs are called residual plots, and they help us determine if a linear model actually fits a set of data. When our residual plots show us a good fit is when our values are close to the x-axis and they're randomly distributed above and below. Reason we want them close to the x-axis is our x-axis stands for 0, or a residual of 0. That means our actual data point matches our predicted data point perfectly. That would be the hope, is that all of our points match perfectly. Now, in most linear models, that's not going to happen. So we're going to have a little bit of leeway above and below. Generally, we want our residual values to stay at about plus or minus 1. So we don't want to get too much farther out of that, otherwise our linear model is not going to give us super accurate prediction. And then we want to make sure that they're distributed above and below the x-axis. So if all of our values fell above 0, that means all of our predictions are above the actual data points and our line is probably too high. If all of our predictions fall below, then that means our line is too low for the actual data. So overall, we want to stay close to the x-axis with some above and some below. This first one is a good example of a residual plot because we only go up and down by a half. All of our residual values are in between negative a half and a positive a half, so that's going to end up super close to the x-axis. This second one, not a very accurate prediction because we're getting values as high as 2 away and as low as negative 2.5 away. So our data is not matching up very well with whatever predictions we were making. So going back to this problem that we had earlier where we found the residual values, here is the residual plot for our data. Determine if it is a good fit or not for our particular data set. This one shows it is not a good fit. Again, we're getting residual values that are about 2.5 away from our actual values. So that's not really a close prediction. Our values are not close enough to the x-axis. Next thing we're going to talk about is making predictions. When we make our predictions within our data, again, that's called interpolation. So within this picture, it's showing domestic airline travel, and it's being modeled with the equation 47.87x plus 1,345.4, where x is the number of years since 1975. Our goal right now is to predict the number of miles for 2003. In order to do that, the first thing we need to figure out is how far away 2003 is from 1975. And 2003 occurred 28 years after. So we would plug into our equation and say y is equal to 47.87 times 28 plus 1345.04, and that is going to give us an answer of 2,685.4, and then that's in thousands of miles based on the labels for y. So that's interpolation because 2003 fell within our data set. Extrapolation, the process is the exact same as interpolation, but now we're just predicting outside of our data set. So now we're predicting for 2019, which happens after the graph is over. So we're going to take again and say y is equal to 47.87 times 2019 happened 44 years after 1975, adding on our 1,345.04, and that's going to give us an answer of 3,451.32 thousand miles. So interpolation and extrapolation simply mean plug into your equation and make a prediction. Go ahead and try this one on your own, predicting the number of miles for 2025 and also determining if it is interpolation or extrapolation. We get an answer of 3,738.54 thousand miles, and it is extrapolation because it is after our data set. Last thing we're going to talk about is causation. Remember, this is determining if our inputs are directly causing our outputs to happen. So a student found a positive correlation between the numbers of hours of sleep his classmate got before the test and their test scores. So what that is saying is more hours of sleep before the test, higher test scores. Can he conclude that he will do well on the test if he goes to bed early? Defend your answer. So the first part is saying yes or no. He can guarantee that if he goes to bed early, then he will get a good grade on his test. The answer for that is no. This is not a causation. And then what it means by defend your answer is you need to give some reason that this might not happen. So, this is saying that the only reason that you do well on a test is because you go to bed early. So a defense of your answer could be that studying also affects test grades. Or what he eats might affect his test grade. Or who he sits next to might affect his test grade. or the pencil that he uses might affect his test grade. Tests are more than just the number of hours you sleep. So you need to give some other logical reason that he might do well on the test other than him going to bed early. That is how you could defend your answer. Go ahead and try this one on your own. Again, this is not a causation. Couple of different things you could have said. People could move into the city that don't have cars, or people who are currently in the city could buy more cars. So they could change without actually having this direct relationship change. If you have questions about this or anything else from the lesson, please let me know when you get to class.